Welcome linear algebra fans, a video on matrix inverses and systems of linear equations. So we'll start with a motivating example where we actually use what ends up being the inverse of a matrix to solve a linear system of equations. We'll then go ahead and define the inverse carefully and talk about how to find it, and we'll close by seeing some properties of the inverse. So here's the system of linear equations associated with archetype B. Last time we saw that solving the system of linear equations is the same as solving the vector equation ax equals b. So we sort of know how to do this. We can pick off the matrix A. It's the same as the coefficient matrix of the linear system. And we can pick off the vector B. It's the same as a vector of constants for the associated linear system, to write the vector equation ax equals b. So here is that A and here is that B. Now, completely unmotivated, we're going to go ahead and consider a different matrix. That matrix is called capital B, and I'll have you work this out on the worksheet, but just use our matrix multiplication from last time to compute the product B times A, where capital A is the matrix of coefficients from the linear system. Okay, so here's what you should get. You should get a really interesting matrix, a matrix with ones on the diagonal and zeros elsewhere, which we know is called the identity matrix. Okay, so again, this is just matrix multiplication, linear combinations of the columns of B with those different columns of A. So since B times A is a special form, it turns out we can use B times A to solve the associated vector equation. Okay, so in order to do that, we'll just start with our vector equation, ax equals b, and then left multiply. Remember that multiplication on the left or right matters sometimes, usually, by the matrix B. So here's what that looks like. We'll just take our vector equation ax equals b, multiply on the left both sides by the matrix B. Now, of course, we know that matrix multiplication is associative. So B times AX is the same as BA times X. And now, since BA is the identity, this vector equation becomes I times X equals B times B. Of course, anything times the identity just gives you back that thing. So here is our solution, X equals B, capital B, the matrix times B. Okay, so we can go ahead and write that out, and here's what you get. B times B is exactly minus 352, which, as it turns out, we know is the solution of the associated linear system. Okay, so a couple questions you might be asking. Does this always work? And the answer is no. Can we determine conditions when we can use this algorithm? And the answer is, of course, yes. So that's mostly what we're going to be doing today. Okay, so let's go ahead and talk about the matrix inverse. Here's the definition. If A and B are square matrices of size n, such that A times B is the identity and B times A is the identity, then we say that that A is invertible and B is the inverse of A. And again, our notation here is that we write B as A to the minus 1 power for the inverse. Okay, so again, with this notation, many properties of the inverse we'll see later arrive in the form show that B is the inverse of A, right? So we go back to exactly this definition and start with B times A, do a bunch of legal mathematical operations, and end up with the identity matrix. And that's how we show that a matrix is the inverse of another. As we'll see in our next section, it turns out that B times A is the identity if and only if A times B is the identity. So we really only need to check on one side to verify that a matrix is the inverse of another. Okay, so just to see that not all matrices have inverses, let's go ahead and have a look at the linear system AX equals B for an arbitrary B and the coefficient matrix A associated with archetype A. Okay, so we'll start by supposing that there's an inverse, and we'll go ahead and sort of manipulate the associated vector equation, again, for an arbitrary B in the same way. So it looks something like this, just like we did before, left multiplying by the matrix B, reassociating B through matrix multiplication, and then we've assumed that A is invertible with inverse B, so X times B times A on the left will just be the identity times X, which just gives us back X. Okay, so we ought to be able to solve the system in the same way. However, it turns out that for this particular coefficient matrix, we've seen that there's a B that our linear system has no solution, right? We found for this particular B, the B1, 3, 2, that reducing to row echelon form leaves a pivot column in the last column. This is indicative of an inconsistent system, which gives us a contradiction to the assumption that A is invertible. Okay, so it turns out that this A has no inverse. Okay, so let's talk a little bit about computing the inverse. We'll go back to our the 2x2 case, and I won't prove this theorem, but it turns out in the 2x2 case there's a handy formula and condition for computing the inverse that you may have seen before. So condition for invertible is that A times D minus B times C may not be 0. And when the matrix is invertible, this turns out to be the formula for that matrix inverse. Now, generally speaking, there's not such an easy formula for the inverse, but it is a real handy thing for the 2x2 case that I'll mention. This is a theorem in the textbook. I'll have you read this, and for the most part, we're just going to use this on occasion. In the more general case, let's go ahead and think about the coefficient matrix associated with archetype B to get an idea of how to compute the inverse. So if our matrix is invertible, let's go ahead and assign the inverse to be the matrix C and recognize that B times C had better be the 3x3 identity matrix. Okay, if that's true, then we can use matrix multiplication to recognize that B times C1 has to be the first column of the identity matrix. B times C2 has to be the second column of the identity matrix. And B times C3 has to be the third column of the identity matrix. Okay, so if we know those three matrix vector equations, we can go ahead and just solve the associated linear system, where here E1 stands for the first column of the identity matrix, E2 stands for the second column, and E3 stands for the third column. So again, the way we do this is augmenting B by the first column of the identity matrix, reducing to row echelon form, here's what we get. Augment B by the second column of the identity matrix, reduce to row echelon form, here's what we get. Augment B by the third column of the identity matrix, reduce to row echelon form, and here's what we get. So therefore, it ought to be that the inverse has a first column given by minus 10, 13 halves, and 5 halves, a second column given by minus 12, 8, and 3, and a third column given by minus 9, 11 halves, and 5 halves. And that, as it turns out, I'm not sure what this P is doing here, that's a typo. That, as it turns out, is exactly the matrix C that we saw before. Okay. So as it turns out, this process always works, and when we say always, of course, there's a theorem, and this is the theorem. I'll just have you read the proof, but we'll work on the take-home message. When a matrix is non-singular, right, of course, one of the consequences of non-singular is that we reduce to the identity matrix. What we do in practice is augment our matrix by the identity matrix and reduce it to reduced row echelon form. Okay, what we'll end up with, because the portion A reduces to the identity, is just another matrix on the right of that portion A, call it J. And it turns out that the matrix J is the matrix such that A times J is always equal to the identity, right? So this matrix J is the matrix with all of those columns C from our last example. Okay, so because we're multiplying on the right here to get the identity, we call J the right inverse, but as it turns out, we'll see this later, that is the inverse. Okay, so J turns out to be A inverse. We haven't yet shown that that multiplying on the left by J also gives the identity. We'll show that one-sided inverse is enough later. And it turns out we haven't yet addressed the case where A is a singular matrix. It turns out that A is non-singular if and only if A is invertible. So such non-singular matrices, as it turns out, have no inverse, and we'll see that later too. So here's an example for you to work on, probably by Sage or some other computational software. This is in the worksheet. Let's go ahead and use row operations, augmenting B, this matrix B that we know has an inverse because it's non-singular, by the identity, reducing it to reduced row echelon form. And what you should get is exactly that matrix that we just saw as the inverse. Okay, so this is what it looks like when it's in a reduced row echelon form. And again, what you do is sort of pick off those columns to the right of the identity, right? This is an n by 2n augmented matrix, and that matrix, as it turns out, is exactly the inverse that we're looking for. Okay, a couple properties of the inverse, and once again, many of these properties are stated of the form show that B is the inverse of A, the way that you do it is by starting with the inverse and then proving that the matrix in question is in fact the inverse. So I'll go ahead and go through this second one, this theorem SS, that tells us that the inverse of a product is the product of the inverses in reverse order. So we'll go ahead here and start with B inverse times A inverse times the matrix AB. Okay, and once again here, we'd like to show that the matrix B inverse A inverse is the inverse matrix for AB. Right, so we'll start with that matrix and see what happens. Now, of course, we can reassociate our matrix multiplication here as long as we keep things in order. Now, since we've assumed that A is invertible, A inverse times A has to give you back the identity. And of course, the identity multiplied by anything is just that thing. So it turns out that this becomes B inverse B, which is also the identity. Now, technically speaking, we haven't shown that one-sided inverse is enough, so we'll go ahead and go through a similar argument multiplying AB on the right by B inverse A inverse. Hopefully you'll agree that the process is sort of similar here, and we end up getting the identity once again. So again here, matrix multiplication is associative. B times B inverse is the identity. The identity times any matrix just gives us back that matrix, and A times A inverse is also the identity. Okay. It turns out that the matrix inverse is unique, and that the inverse of the inverse is the matrix itself. A couple other properties, I'll have you prove that when A is invertible, the transpose of A is also, and it turns out that the inverse of the transpose is the transpose of the inverse. And it turns out that when A is invertible and alpha is any scalar that's not 0, then any scalar multiple of A is invertible, and the inverse of a scalar multiple of A is 1 over that scalar times A inverse. Okay, so again, I'll have you do this theorem MIT on the worksheet. Check it out. But that's it for this section. So let me know if you have any questions, and have a great day. Bye-bye for now.